Okay? So as we push to larger and larger rings, we'd stop looking at it, or we'd start looking at more and more as an ether instead of these fancy names for these. So you get a bunch of different names for the smaller ones. The epoxide is an alternate name for an oxyrane or a three-ring system, okay, including that oxygen in the middle. Okay? They're typically very reactive, but they are commonly found in nature. Why might they be very reactive? The epoxides, that is.
Does that do the angle strain?
We've got massive, good thing I made this picture nice and small, we've got a lot of angle strain in between those bonds. Okay, why? What's the hybridization of that carbon? It's sp3. What's the bond angle on an sp3 carbon? We're looking at 109.5. What's the bond angle in an equilateral triangle? 60. So we went from 109 degrees where it's happy to now forcing it into a 60-degree bond angle. Not a particularly happy system. So there's a lot of strain in that. One of those bonds is much more is prone to break open. So that's one of the things that we'll take advantage of when we're looking at epoxide reactivity. Okay. There's two methods to name, just like we've got with our ethers. We can treat the oxygen as a side group, okay, or as an extra little piece to it, a substituent, or we can name the ring as the parent. Okay, so if we look at the oxygen as a side group, we'd go through and find our longest carbon chain, which, if we're looking at this one, we've got, what is it? 1, 2, 3, 4, 5. Oh, we would have to go across the other side. Why? As opposed to counting back in this direction. When we go through and number, we want to make sure that where our alcohols are would show up within the parent chain, or the main chain length. If we doubled back, we've removed one of those oxygens as far as its reactivity. So we could name our parent chain. We've got our 5 carbons, 1, 2, 3, 4, 5, which leaves us with pent. Okay. In this case, we're naming the oxygen as a side group, okay, or a substituent on it. So what's our ending going to be for our pent in this case? Pentane. Our oxygen is a side group or a substituent, so our main chain is based just on what else is in it. So we've got the pentane for our main name. We can then identify our substituents. Okay, what do we have as our substituents? We've got meth, eth, and this is where we come up with our epoxy. Okay. Number 2. Wait a second. Did I do this wrong? I might be doing the nomenclature on this wrong. I thought I had this. I'm going to have to review the nomenclature, actually. I'm sorry. I'm pretty sure I didn't put up the answer for it. No, I didn't.
Would that be oxyrane? You have carbons on the ring, don't you? And then you have to name all the
Yeah, so where I was going with this was that we would have 2, 3 epoxy, pentane, and then we have our ethyl and methyl thrown in there as well, just to make things fun. We'd have our 2-methyl, 2-ethyl. But that name doesn't seem to match either of those, does it? I'm like 90% certain that's how you name it, or that's one of the names, and I think that's the common name on the left. So I'm not quite sure what those directions are meaning. The other option is that we use our ring as the parent structure, and that's where we can call it the oxyrane. So our oxyrane is the very end of our name, and then we'd name all the substituents that are attached to it. So we would have a... Oh, really? Wow, it was. a dimethyl, and a diethyl oxyrane. And we'd have to go through and number those probably by priorities. So it might very well be 1,1-diethyl, 2,2-dimethyl oxyrane. I think I've got those two names right for both those methods. Those directions don't seem to match that though. Okay? So just kind of be aware of that. You want to review your nomenclature with your epoxides a little bit more carefully. I can tell you right now, I'm not going to test you on epoxides. Okay? As far as nomenclature goes. I'm more concerned about their reactivity, which will kind of end there. So when we're looking at our reactivity, you want to identify where you've got that likely chemistry. Our likely chemistry, again, we'll go ahead and just highlight it in red because we are done. We're looking primarily at those carbon-oxygen bonds. Why those two? Okay, we do have strain, but there's also strain in that carbon-carbon bond. That angle strain is all the way around that. Why are the two red ones more likely to be broken or made for that matter? The polarity of that oxygen. That oxygen is electronegative, drawing the electron density in those two bonds to one side or the other. That polarity is what we're going to take advantage of when we look at the chemistry for our epoxides. Okay? Just like we've been doing for the ethers and the alcohols, the same general idea. Okay? Please review the epoxides, so chapter 14, over the weekend. Yeah, you can definitely pack